Good morning, everyone, and thank you so much for joining us for today's Nexus Leadership and Innovation webinar series. My name is Liz Mahalski, and I'm a program manager here at Nexus at Michigan Engineering. A little bit of housekeeping before we begin. You are welcome to ask questions throughout the presentation by putting them in chat or raising your hand via Zoom, but there will also be a dedicated question and answer period following the presentation. It is now time to welcome today's speaker, Richard Rood. Richard, or Ricky, Rood is a professor emeritus of the climate science at the University of Michigan. Prior to that, he was a scientist and a science manager at the National Aeronautics and Space Administration. His recent research has been on the use of scientific knowledge in climate adaptation, and he developed several courses on how to manage the problems caused by climate change. In addition, his research publications, he is co-author with Andrew Gentleman of Demystifying Climate Models, a User Guide to Earth System Models. He writes the monthly column Climate Blue for Michigan Today, and his articles have appeared in The Conversation, Scientific American, and Washington Post. I'll turn it over to you, Ricky. Welcome.
Okay, thank you. And thank you, Nexus, for hosting this webinar. What I'm going to do today is to describe the course concept and the initial outline of a course on what I would call climate change problem solving that follows from the classes and the curriculum that I developed in my time teaching at Michigan. And right now we're calling this Managing Climate Change Consequences. As Liz said, I was a scientist and science manager at NASA from 1983 to 2005, working primarily on modeling and supercomputing. But I also had several stints of being an advisor to other agencies and spent some time at the White House Office of Science and Technology Policy on modeling and supercomputing. In 2005, I moved to Michigan as a professor in the Climate and Space Sciences Department, then the Atmospheric, Oceanic, and Space Sciences Department, as well as I was appointed in what was then the School of Natural Sustainability and the Environment that became SEAS. And in 2023, I retired to actually focus on things like writing and developing these sorts of material, because I think it's a really important thing for me to be doing with what I think is a unique set of resources and skills that I've developed over the years. So what I want to do is to divide the talk up into something that is like the 4 modules that are currently planned for the course on climate science, the introduction of problem-solving skills and non-stationarity, the uncertainty, the important role that uncertainty plays in problem solving, and then to introduce this concept of scenario planning and uncertainty management. I think it will be a little bit different than probably other material you have seen on climate, including the discussion of climate science, because one of the things that I've done over the years is I have taught and I have consulted with people from just about every discipline. And so one of the things I try to do is to play at the interface of science and the disciplines that other people are interested in. The original goal of the courses was targeted at professional masters who wanted to incorporate climate knowledge into what they were doing in their profession. And by professional masters, not only engineers, but public health, urban planning, a lot of students in urban planning, and the list could go on. Climate change really touches everything at this point. So I'm going to start with the climate science part of it. The Earth is observed to be accumulating energy, heat, and the most convincing evidence of that is the heat content in the ocean, and the heat in the ocean is just increasing. And because of the accumulation of heat, we're at a point that sea level is rising, ice is melting, and by ice is melting, I mean the glaciers that have been fairly stable on land, as well as the ice sheets of the North and South Pole. The average temperature of the surface is increasing. The precipitation extremes are increasing because they follow the temperature, and the weather is in general changing. So when we look at the ocean heat content, what you see over on the right of that is a time series from the 1958 to, in this case, I think 2022, of the heat content in the ocean measured in 10 to the 22nd joules. So this is a lot of heat. And if you want to think about heat content, a good comparison would be to imagine heating and stirring a pot of water on the stove. And the amount of energy in the pot increases. Some of that energy raises the temperature. Some of it causes motion in the pot. So you can think of the ocean as this pot that's being warmed. Heat content, motions are changing. And if you look at this from about 1980 to 1990, you can see that in the previous record, and this record can be extended back further with different sorts of proxies, this sort of variability that was very common becomes small compared to this signal of increasing heat content that looks like this. And this is a large, mass of water, a large body of heat. And so it doesn't change a lot from year to year. And so it's a much better measure of what's going on than the temperature in the atmosphere. But here is the temperature in the atmosphere. This is a type of plot that you probably see more frequently, which shows in this case from 1880 up until 2020, the temperature of the global surface temperature. So this is an average global temperature. And it's compared to an average taken from 1951 to 1980. And one of the things that you see here is the emergence of, again, this trend in about 1980, 1990 time frame of continual rising over this sort of global average. And again, in this case, these are averaged over each decade. And this averaging process is one of the ways that we manage the interannual variability that is more commonly associated with weather. So if you look at this, we are already more than 1 degree centigrade, 1.8 degrees Fahrenheit warmer than a pre-industrial temperature, which we now take to be from about 1750. And there are many regions on the planet that are above 2 degrees centigrade warmer. Each of the last 4 decades has been warmer than all the previous decades, and this can be extended back actually for hundreds, a small number of thousands of years, perhaps at this point. Excuse me. The last month that was below the 20th century average, so rather than the 1951 to 80 average for the whole century, was February 1985. So the chances of this being some sort of random occurrence is infinitesimally small at this point. And if you look at when you were born, I don't know what the age of this audience is, but the median age of the world is 31 years, between 31 and 32 years. And that means that well more than half of the people on this planet have never been on this planet in which the temperature was below the 20th century average. There have been places, months here and there in different places. Michigan had a couple that were cold. But when we look at a global average and we look at time average, it's been a very long time since we were below that 20th century average. And this is expected to continue. We are not doing anything right now that would take us off this path for at least the next 30, 40, probably 50 years. So we will soon exceed the 1.5 degrees centigrade goal of the United Nations Paris Convention. In fact, for the last 12 months, we've been above that, but we'll probably drop back down below that for a little while. But then the trend will continue and we will soon exceed this. I feel quite confident in the next couple of years. We have this warming. If we make this more locally and come to Southeast Michigan, what here are a couple of temperature plots, and the bottom one is from 1951 to 1980. The top one is from 1991 to 2020. This is a histogram. Here is fitting a bell curve to those histograms. And what we see is that the more recent 30-year period, again, is quite a bit warmer than 1951 to 1980. You see that over here with the shift of the peak going from the older 30-year time period to the most recent one. And it's not as obvious in this picture as in many others, is that the spread here has increased a little bit as well. But one of the more interesting aspects, consequential aspects of this, is that if you look at this line here, which is the freezing line, and this is for January. Sorry, I did not mention that earlier. This is the freezing line in Southeast Michigan. In 1951 to 1980, you did not see months that had an average that was above freezing. Whereas in the more recent times, not only do you see months that have had averages above freezing, if you think of these months here, there will be many days within them that are above freezing. So we've seen substantial warming in places like Southeast Michigan, and that warming is largest in Michigan. And as you can imagine, when you cross the freezing line, there are many, many consequences there in terms of precipitation. If you're running winter businesses that are relying upon it being cold, you have many consequences there. And as a curiosity, the most interviews that I've ever had from the press have been in the last year when ice fishing in Michigan became, in many cases, not possible. So if we take it, sort of put all this together, and this is a plot of where does this heat go, 90% of the heat goes into the ocean. So going back to my first slide that had a picture on it, here is your ocean heat content. So 90% of this heat is going into the ocean. 4% is going into ice, the cryosphere, 6% into land, and 1% into the atmosphere. So one might imagine at this point is that the atmosphere is actually the most variable and probably the least desirable from a scientific perspective place to measure this warming. Yet you can see on an average that warming is emerging as a signal. Generally, the signal has emerged in many variables sometime around 1980 to 1990. And in many instances, that warming signal is increasing more rapidly now than it was 20 and 30 years ago. That is, we are seeing a lot of important consequences that might in fact be accelerating. So scientifically, this is a very simple problem. It's the principle of the conservation of energy. And what we do is we take the Earth and we count the amount of energy coming in from the sun, the amount going out. And if there's a stable climate, then that balance of energy coming from the sun and energy going back out into space after it's sort of been processed and churned and some of it stored in different places like the ocean and the planet, if the climate is stable, then that energy going out is equal to the energy going in. And again, it's fairly simple in the sense that the only thing that can happen to the energy from the sun is that it is absorbed or it's reflected. And, and so when you think about how is climate changing, or thinking about things like geoengineering, what we think about is how do we change absorption and reflection. And the heat energy is emitted by the surface in the atmosphere. And what climate science is at some level is measuring, monitoring, analyzing, predicting this energy balance and how it will change. So in our warming climate, in our present climate, the Earth is accumulating heat. We are out of balance. We are warming. And we know by calculating budgets of how different things that absorb and reflect are changing things, that the primary cause of this energy imbalance, this accumulation of heat, is by increasing carbon dioxide and methane in the atmosphere. So this concept of balance is one of the things I think is most important when we're reaching across different disciplines. And balance is relatively, simple to think about to start with. Here's the sun. I put an earth out here, then I put an atmosphere around the earth because it's an insulating blanket that can hold the heat close to the surface. Because we're really interested ourselves in what's happening at the surface, you need to focus on the surface. And carbon dioxide is making this blanket thicker so that it has more time to hold heat down close to the surface for it to accumulate. But balances are not just static things. Some of us are familiar with, something like what I've drawn here, which again is time. And I have rabbits or hares and lynxes or bobcats. And if you look at the population of the two, you'll often see that the population of hares will increase when the population of lynxes is low, and the lynxes go up, the hares come down, and you can see this sort of thing that you see in a lot of ecological systems of dynamical balances, as you have here two opposing forces. So balance is not static, and the climate is not static. We see things like the ice age cycles and things like that, and those things will be at some level some attribute of what we might consider a more dynamic balance. And balance can be precarious. Here's a skilled acrobat who's standing up on a tight wire, and the acrobat here, if there are disturbances, the good acrobat there is able to accommodate those disturbances and remain balanced by, say, moving the umbrella, managing the center of gravity of her arms and legs, and so has the ability to accommodate disturbances through feedbacks that help maintain the balance. So I just made connections to ecosystems and acrobats. And for a lot of folks, thinking about balance and thinking about Earth's climate, I propose one of the most straightforward is the household budget. One that's also emerged in my classes a lot is people think about their health, and they think about this idea of what they call in health sometimes homeostasis of the body being stable. One that has proven especially effective, especially since COVID, is think about supply chains, something that is in a balance, but that a small disturbance can change. Other things more climate related is how much water is in the oceans or the Great Lakes. And then we're always dealing with balances in economy, our economy, and balances in power. So this idea of balance, I think, is central to thinking about climate science, and the balance there is the Earth's energy budget. So balanced systems are common. They're often quite familiar. Some people spend their lives managing them, whether they think about it consciously or not. And if they are disturbed, they might accommodate the disturbance and regain the balance. They might collapse. They might move to another state of balance. we would call one of these negative feedbacks, one positive feedbacks, and the other positive and negative feedbacks, which might become a dynamic balance. And sometimes people talk about chaotic systems. But what we are doing is we are altering the Earth's balance by warming it. There are positive and negative feedbacks, and they are intentional with each other. Ultimately, if we warm too much, it's quite clear that the positive feedbacks are ultimately stronger. So that's one of the reasons we worry about limiting warming. And the climate is warming, changing, and it is said to be non-stationary, which means that the average and the variability are both changing. We presume right now we're headed to another state of balance, but that is minimally decades into our future. And because of that, we really need to be thinking about how to adapt and to live and work in that changing climate. What are the consequences of this? I often list, that, we're seeing more coastal flooding, we're seeing more heat waves and things like that. But this past few months have been really quite interesting in Houston, Texas, where they had more than 2 feet of rain in a couple of events in the region. And that has become so common that that really didn't even get reported on much. And so in May, they started, a major flooding after 2 feet of rain, essentially. Already in 2024, there was that event. There was Hurricane Beryl recently. And so one of the things we're seeing in places like Houston is this sort of chronic flooding. And we talk about these 1 in 500-year events. I mean, here's an event, if we were to plan for it, it was going to happen once in every 500 years. Houston has had, I think, upwards of 10 of these events since 2000, most of them since 2005. So when we think about something like this, Houston is sitting on the Gulf of Mexico, which is getting warm, exceedingly warm this past year or so. So for when there's water there to evaporate, for every degree locally that the air is warmer, there's a 7% increase of the moisture in the air. And that leads directly to the intensity of precipitation increases. And if you have sort of a constant supply of water, as Houston does, and actually has Michigan often does, actually from the same place, the Gulf of Mexico, you can get the accumulation of water, and you can get chronic flooding, and you can get all sorts of challenges that come from what we might call water abundance. So globally, we are experiencing heat waves, new extremes in flood and drought. We're experiencing sea level rise. We're experiencing changing in storms everywhere, all the time. And I think it's safe to say we have a problem here to deal with. So I just want to briefly touch on some problem solving skills, some of the ideas that would be introduced in this course. So language wise, we have sort of two responses to this problem. One is that we can adapt, which means that we can, see the problem coming. We can maybe anticipate it coming and do things to provide us more resilience, or we can, experience the flood and rebuild. Or we can experience the heat wave and, what are the consequences of the drought. But we have to adapt to this. And I just list here a whole bunch of ways that different scales from individuals to global can think about adaptation. The other response that we have, point I would like to make, is these are problems that we've really always faced. And this is another important thing, I think, in the framing, is that climate change is not exactly bringing us new classes of problems. It's amplifying the sorts of problems that we've already had, that we have in fact built perhaps to be able to deal with, And what we've built, how we behave, is becoming less and less effective at dealing with climate change. So what we have to do is to think about how to do these things differently, but we're not walking into this sort of with blank experience. The other response here is to mitigate, which we also must do. And mitigation is generally viewed as the reduction of carbon dioxide, methane, the other sources of warming, to keep it from getting too hot. And it's too hot to adapt, or it's too hot to um, you know keep ice sheets from collapsing or releasing a lot of methane and carbon dioxide that's stored in permafrost. There are just many reasons that, from the perception of human stability, we need to mitigate and keep it from getting too hot. And this is a really hard problem. These are major transitions in energy systems, economics, and what I think is the most challenging, personal behavior. And they're difficult and time consuming. And we need to appreciate that we have the opportunity that small changes can accumulate into big differences here. But we are not going to just have a magic solution that suddenly we are not emitting carbon dioxide and methane in dangerous levels. So one of the skills that I think is important in managing big problems like this is to give yourself a framework for thinking about them. And one that I often use is to think about how big an area, what's the spatial scale, is it local or global? I think about, is it a problem that's near term or long term? And then wealth is really important because wealth talks about your ability and sometimes your desire to deal with the problem, and it's also linked to ethical issues and social justice. But if you think about a problem along these different axes, then you can start to think about, where can I get a grip on how to deal with some of these things? So the scale for mitigation to be effective is global and long term. And as a global long term problem being connected to wealth, this is the most difficult problem that we have on our portfolio in climate. So that is one of the reasons why, if you look at the last 20 or 30 years where we've known we need to address this problem, and any effective addressing that we've had has been sort of slowing and keeping it from being as bad as it could have been, but we're still increasing emissions. This is why this is just a very hard problem. But if you look at adaptation, it can be near term, it can be local, it can be even individual. And it's probably best that not all the efforts are individual, but as a near term local problem, the cost benefit can be clear and the degree of difficulty can be, compared to the global mitigation problem, relatively low. And it's essential that we do this. And so that's one of the reasons that I want to focus on adaptation as much as I do. Also, we can plan on 30 to 50-year time spans. We do it as communities, as cities, perhaps even as corporations. And we can do this on what I ultimately call appropriate regional scales, but from individual to local spatial scales. So you have a lot more ability to address problems and deal with them with adaptation. Another skill I think is important is to place climate change into context. One of the things I said earlier, here's climate, this upward trend in temperatures. It's related to carbon dioxide and methane. And if we think about what's carbon dioxide, the carbon dioxide is coming from energy, and 70 to 80% of our energy consumption still comes from fossil fuels. And this is a very stubborn number. One of the problems is globally energy use is increasing, and it's coming from the fossil fuels. There's a huge amount of new renewable energy, especially in developing countries, that if we, one, didn't have, the problem would indeed be quite a bit worse. But it's still in tension, perhaps in balance with energy coming from fossil fuels. Um, some really positive news. There is, in fact, at this point, some evidence that emissions could peak and start to level off and maybe even decline this year or next. I think that will be one of the most important pieces of mitigation news that I have seen and experienced if that were to occur. But one of the things I want to do here is just point out here's a relationship between climate, carbon dioxide, and energy. And once you're related to energy, you're related to something that's critical to our economy, something that's very aligned in international power, corporate power. And I can keep doing this, but in the standard of living, population, social justice, economy, consumption, our desire to consume, and that our economy is based upon consumption and wealth. And the question becomes, how does climate become a priority with all of these other things that are perhaps more compelling, more short term, urgent priorities? We can look at instances where we've had energy insecurity. We can look at instances where we've had economic insecurity. Anytime we have had those in the past, climate change is usually become subservient to addressing those things. We go, well, we have to keep doing this in order to keep our energy and economy going. And if we extend this more broadly, climate sits in relationship with health security and national security. And so the context is that climate change and climate is in relationship with all of these other problems, many of which can often take priority. So one of the goals of the climate change problem solver is to keep attention on these problems in the presence of many other important problems. And one of the biggest challenges in the United States and many other countries that are democratic is keeping attention on the problem through elections. And then I want to introduce this idea of non-stationarity a little bit more formally and some of the consequences of that. So I've reproduced this figure here and just drawn this line of here we are in a warming climate. I drew it, extended it out here because again, until we are effectively reduced most of our carbon dioxide emissions, this is going to keep warming. So we have decades of this on our agenda. And then over here, I took that Southeast Michigan, and this is for an annual average, and broke it down into decades, 1991 to 2000, 2001 to 2010, 2011 to 2020. And, one could argue, statistically, we've got some issues here of sampling. But the point I want to make is you can look at this on decade by decade, even on a regional scale right now, the climate is changing. And that really, this idea of non-stationarity, that we are working in a changing thing, challenges. How do we plan for recovery from a flood if we're going to, like Houston, have another one in another month or two? We can't keep doing what we've been doing. How do we design future bridges and pipes? Where do we put new construction? Is it smart to rebuild in the same place, or do we need to be thinking about intelligent ways to spread out and move some of our activities and assets and resources? How do we plan? We have this problem that old weather specifications and standards are no longer correct. The most recent ones, which we might imagine using, are not representative of the future. In the United States right now, about 80% of new building is not considering climate change, which is considered a liability in multiple ways. We know the temperature is rising, precipitation is all over the place. Really, what's robust is the variability is increasing and sea level is rising. And there are many other measures of climate and their interface with humans and ecosystems that are changing very rapidly. So the short answer is we don't know how to do this in reliable standard ways at this point. However, we are compelled, I think, to learn to live and work in the climate, in a changing climate. So that puts us straight up with the challenge of uncertainty. How do we deal with uncertainty? And we have, again, something of a dichotomy or a contradiction. But first, I want to say uncertainty poses many challenges. It always does. This is not unique to climate. So if you go into the climate problem, you say, well, it's so uncertain. If in fact you look at the uncertainty associated with climate, it is likely to be the most certain aspect of what you're dealing with. So on one hand, there's great certainty in this warming, increased variability, more intense precipitation, melting reservoirs of ice, sea level rise. These things are certain. So we know that change is occurring and going to keep occurring and keep increasing. But if you look at the sort of information you would like for planning your community, what's going on at a certain place at a certain time. One, the current models are really not up to that, but from a practical, even theoretical point of view, there's really limited information that can be provided for a particular place and time. So you have to figure out how to manage this uncertainty. Why is this such a challenge? Well, one, because one of the things that is certain is that variability will increase. So, if you're thinking about a pendulum or something, it's rocking more. So you have to accommodate different extremes. And the other is the non-stationarity itself is large. We are not specifically modeling right now sort of the details of the non-stationarity, and it's an extraordinarily difficult problem. So the non-stationarity is large, so you can't just imagine developing new statistics for 30 years from now with the idea that they are stationary statistics, because you're still there with it changing. So the one thing that is certain is change, which is, of course, something of a universal truth. The other aspect of uncertainty is that it's used to confound and disrupt. And I'm not going to talk about that today. But uncertainty is used with this idea of we must be certain before we can make decisions and spend. And there's a certain fallacy in this. And one of the points is that uncertainty must be managed, but you need to be aware of how uncertainty is used in communications and in taking political positions. So, how to manage uncertainty is one of the most important and time-consuming aspects of dealing with problems like this. So I want to finish with this idea of one way to manage uncertainty, scenario planning. And the idea of scenario planning is something that we have been working with at Michigan to develop a way to manage scientific uncertainty and to place scientific uncertainty in context with other sources of uncertainty. And what we do is to develop plausible storylines of what climate change means to me and the problems I'm facing. So it's really important to now start to think about what does climate change mean to me, my community, my corporation, my organization that I have influence over. By plausible, they need to be physical. They need to have some degree of realism. Science fiction is great, but it's not what you need in order to plan, design, and to make decisions. And one of the ways to sort of keep it real is to come back and look at vulnerabilities that you might have already experienced, your community might have already experienced from weather. And then you need to develop these stories or scenarios using some rules and tools drawn from climate science. The idea is you develop a set of stories that span the uncertainty for a specific vulnerability or management decision. So one of the techniques here is always trying to make this concrete and specific and getting away from, well, climate change will increase floods and droughts. Climate change could do this and that. Make it real for you. And then after you have these stories, there are different strategies for using the models that can give you some quantitative guidance for design criteria decision making. So here are just some of the rules and tools that I've developed. I've been writing about them in my Climate Blue column for the last 6 to 8 months. So I have 3 rules at the top: the rule of complexity, change, and continuity. The first one is that there's no one thing climate change will do, no single outcome. The second is addressing this idea of non-stationarity, that you have to plan on a 30-year time span, but with the idea that in that 30 years, things are going to continue to be changing. And the other is, if it used to happen, it will likely continue to happen, which I think of, they're big hurricanes, small hurricanes, fast hurricanes, wet hurricanes, dry hurricanes. You will still have all of those different types of storm, and climate change will affect all of those. And to get sort of wrapped up in the idea that there's one thing that climate change will do to, say, hurricanes is not especially productive. We need to build from vulnerabilities. You can learn a lot from the surface around you, because a lot of times weather and climate are problematic because of things we have done on the surface. And on the other side of the coin, we're changing the surface, such as sea level is rising. And so a storm that is identical in characteristics to 30 or 40 years ago, if the sea level or the lake level is high, it will have bigger flooding potential. And when I say examine the edges, things are changing faster. Let's say the transition from winter to summer, spring. Look at what's going on in different sorts of edges. So the wrap up. We know the Earth is warming. We need to intervene. We know what needs to be done, but we really don't know how to do it. Our interventions so far have not been objectively effective. It's because it's a very difficult problem. We need to expect decades of warming, which we're going to have to live with, and we must work in this reality. The science part is the easiest. The hard part are political, societal, and cultural barriers, but that's been true with things that people have done forever. My goal is to provide some knowledge to overcome the anxiety of climate change that leads to paralysis and inaction. Use knowledge to recognize and overcome barriers, and then think about sort of the no regrets mitigation and adaptation actions that we can do that are consequential and beneficial. So my final slide, you can have the skills and the knowledge. Climate change provides a usable vision of the future. I would say this is unique in all time to have such a good vision of what the next century will look about. It is your most common knowledge of the future. It could be least frightening. And there are techniques and behaviors to gain control. And if you choose to use this knowledge, you will be better off, more competitive, and contribute to a better world. So thank you.
Thank you so much, Ricky. Does anyone have any questions? The question is, do you see pressure rising for risky interventions?
Yes. One of the things that struck me in the last 2 or 3 years of teaching, that even with my students, they are increasingly comfortable with talking about geoengineering. And, you could see companies setting themselves up, trying experiments. There was one in Oakland, California, that was recently shut down because of local protests. So, one of the things that worries me is this sort of rising, perhaps, reliance on different sorts of geoengineering interventions, especially ones that reflect away more of the incoming solar radiation, which, aside from likely to have enormous environmental consequences and changes to precipitation, also have do not address other issues of carbon dioxide, methane pollution. I don't think we know nearly enough to be taking these on. And I don't think we actually have the tools, either the observations, the models, or the theory, to be making reliable decisions about them at this point. So it worries me to see sort of the rush to these sorts of solutions.
One more question. Could you please share more about the open climate resources and learning materials?
So on Open Climate is sort of my personal website. And one of the things we're doing with the Nexus course is taking some of that material and elevating and updating that material. So on Open Climate, one, there are some articles, but under the classes tab, there are a collection of lectures from two of my classes, well, actually from three of my classes at Michigan. And in addition to that, there are a number of bundles of mini courses. Two of those bundles are sort of 1 to 2 hour introductions of the subject that have been used in classes at Michigan and at other places to introduce the subject of climate change and to try to initiate discussion. They've been used in biology, physics courses, as well as in history courses. And for the last 4 years now, I've had the introductory lectures in a course that the medical school, especially medical students, have designed. So under the classes tab, there are a lot of lectures and things that will be modified and updated and bundled more professionally for this course. Under the resources tab, I have a lot of resources that might help people to address and think about the problem. And then I try to have a fairly large public presence in articles and interviews. So I summarize some of those in blog posts on the website as well.
You covered everything so thoroughly that there's no questions.
Yeah, I understand. Okay. Thank you.
If there's no other questions, thank you so much, everyone, and we hope
Hi,
to see you
Sam.
next.
So.
Have a good day, everyone.